symbol, requirement, and this apparently. Oh. There's the direction with respect to objects, and then direction with respect to each other. So I'm sort of going to lay this out. We'll be doing plenty of examples. All right, so the symbol that I use for friction is what I call a baroque F. It's sort of an F, a little bit of extra curl in it. That's the symbol I use. It's the same symbol I use for frequency later on. Tension, I do F sub T. I used to use capital T, but there is a formula that we'll hit later on in the course in which we need to use period and tension, and both of those at that time was using a capital T. So instead of using capital T for tension now, and then later on going, we're going to change that symbol, we'll just start out using F sub T for tension. For normal, I use a capital Y. And gravitational, well, I use one of two symbols depending upon which gravitational force I'm talking about. I'm either using W for weight or F sub G for the more general formula. And other is problem specific. All right, so the requirements for gravitational force, I think probably the simplest one, I need two masses. That's the only requirement for there to be a gravitational force. Now, if it is weight, I have an additional requirement that I have one small mass, small quotation marks, and one relatively, relative to the other mass, relatively huge mass. Actually, relative to most things. So, for example, a small mass and a large mass in that context would be, an elephant would be a small mass, the planet Earth is a large mass. If I'm dealing with the gravitational pull between the Earth and the Sun, those are not different enough that we would use the generalized formula. Normal force, the requirement is contact between two objects. So right now, my feet are, actually my shoes are touching the ground. There's a normal force between my shoes and the ground, actually in the carpet. There is a contact between your pants or dress and the chair. There's a normal force between them. So why is it called normal? Normal is a math term. What does normal mean in math?
Is it opposite to the tangent? Something like that?
No. Oh. In some sense, yes, it
Or
is.
perpendicular, I think.
Yeah, perpendicular is, I think, clearer. So the normal force is always perpendicular to the surface of contact. I should say surfaces of contact. And since the forces come in pairs, my pair of normal forces, if I'm pushing against the wall, the force on the wall is that way. The force on me from the wall is that way. So the normal forces, the pair will oppose each other. Or they all oppose each other. They are pointing away from each other. So I can add on to here, each force in that pair is same type, same magnitude, opposite directions, and acts on different objects. Gravitational force, it brings things together. The gravitational force on me is downwards, by definition of down. The gravitational force on the earth from me is upwards. So gravitational force will always point towards each other in that pair. And it is from center of mass toward other center of mass. And I'm always questioning whether I need to write it because the writing is so incredibly bad there. I'm not quite sure people can read it, but it slows me down at least.
Dr. Fox,
Yes.
what are the titles of the last two columns?
Direction with respect to the WRT, the objects, and direction with respect to each other. Tension is a pulling force. If you pull on a rope, so a requirement is that there needs to be a tight or taut rope, chain, string, whatever you happen to have. With respect to the objects, it is parallel to the taut rope, chain, string. So we did the rope in the hallway, didn't we? Yeah. So the tension would have been parallel to that rope. Tension in many respects is opposite of a normal force. Normal force is sort of a compression force. Tension is a tensile force, and the pair forces, it's pulling. Things that pull are trying to pull things together. Things that push are trying to push things apart. That makes it better. Friction requires contact and desired relative motion. Often that's thought about if it were frictionless, what would happen? So for example, I push against this table right here. If the ground were frictionless, what would the table do?
Start moving up.
All right. So therefore, friction opposes that. So friction would be acting this way on the table and that way on the carpet. So with respect to each other, friction is, I generally would call this anti-parallel. They're not pointing towards each other in this much sense as they are beside each other in opposite directions. It is parallel to surfaces of contact. And let's see if I can. Yes, so much better. That's That leaves this big gap with other. What is the requirement for other? Other shows up, typically in a textbook problem, other shows up when you don't care what the source of the force is. Forces all have a source that's creating it and a object that is receiving it. So you've got the source and receiver. Other shows up when you don't care or don't know what the source is. And I mean, don't care in the sense of physics, not as in you personally, what you care about. Or don't care or know source. So for example, a 5 Newton force is pushing on a box. What's causing that force? Don't know. It's irrelevant to the problem item. So the direction with respect to the object is problem specific. So in the case of the example I gave, it's however I draw that 5 Newton force, it's a pushing force. And with respect to each other, this is the one time when we'll do what are called force diagrams, and we'll eventually lead up to a test level problem. In the force diagram, you draw the pairs unless there's an other. So even though there is another one, we don't draw it. So don't draw the other force. Questions today? All right. To give you a wider context for where all this fits into anything, the process that I'm going to take you through for solving physics problems is what I refer to as the facades method. These are the steps that I'm going to hopefully have you go through. So F, this is the first step, is the force diagram. So when you're faced with a problem, once it's drawn, you do a force diagram on the objects that we care about. A is for acceleration. You determine the direction of acceleration. Once you have that, you then find once you know the direction of acceleration, you now define the coordinate axes. That's when we did I hat, J hat, that's what we're doing there. D is decompose, or decomposition. I guess I'm doing nouns right now. In other words, if I have a vector, do I need to break it up? And I'm going to break up any vector, any force vector that is not completely in it's not parallel or anti-parallel to either axis. We did that with the projectile motion problems because it was shot off like that, but we defined our coordinate system as vertical and horizontal, so we had to break this up and do horizontal and vertical components. That's what the decomposition is. E stands for equations of motion. Equations of motion does not mean that an object is necessarily moving. These are not the cake formulas or anything from chapter 2 and chapter 3. Equations of motion are based upon F equals ma, whether it's moving or not. Then substitution. There are certain things like weight has a preset formula, so if I have any equation of motion with weight in it, I can take my other formula, stick it in there. Friction has a formula. The generalized gravitational pull has a formula. And over there, that's pretty much it. Later on, we'll have some extra formulas for acceleration in chapter 6. And then the last one is solid. So what we have done so far is from our checklist over there of those 5 forces, we're going to then do force diagrams. And once we've done the force diagrams, then we can start getting into the rest of it. But this is critical throughout this course and the next course. The general bulk of, or the crux of a lot of these problems is to find the acceleration. Once you have acceleration, then you bring in chapter 2 and chapter 3, and you can make predictions about where objects will be at some point in time. And I think on that note, Bryson says it's time to go.
Terrible.